Okay, so today we are graphing a few of the other trig functions. That's why it's called part 1. We are going to be able to graph secant and cosecant. Okay, secant and cosecants were the reciprocals of sine and cosine. Secant with which one? Cosine. And cosecant with sine. Okay, and by that, then the reciprocal means that basically their points were going to basically be flipped. Okay, so if you're looking at page 1 from your notebook, go ahead and open up sine and open up cosecant's flap. Okay, because we already filled in sine's flap, right? No, we're looking at the first two. Now on the golden rock. Flip back. Yeah. There you go. So you got sine on one side and you have cosecant on the other. They're side by side because again they're reciprocals of each other. Okay? So what was the sine of pi over 4? What was the sine of pi over 4? Look at your little table. Give me root 2 over 2. So the cosecant of pi over 4 is the flip of that. When you flip square root 2 over 2, what do you get?
2 over 2.
That is 2 over root 2. Can I leave it like that? Rationalize it. So when you do that, you'll get 2 root 2 over 2. What happens? They cancel out, and so then you're just left with root 2.
Why is it pi over 4? It's just graphing it out.
Yeah, we're just graphing it out.
And I'm saying, why is it like the end of the, oh, never mind. Then because always is, I thought we were doing pi over 2.
No, we're about to go through pi over 2.
Oh, okay.
What was the sine of pi over 2? 1. So if you flip that, that becomes what? 1. 1 over 1, same thing. When you flip it, it's 1 over 1. What was the sine of 3 pi over 4?
Root 2 over 2.
Root 2 over 2. So if you flip it, it's going to be root 2. What was the sine of pi? 0. When you flip 0 over 1, it's going to be undefined. Okay, you can put a slash, you can write UND, undefined. What happens if something's undefined? What's happening if there? It's an asymptote, a vertical asymptote. So at pi, there's actually a vertical asymptote on the graph of cosecant. Yes. And it would also be a negative pi as well, because if you look at the other side, remember we just kind of flipped everything over. So yes, there will also be an asymptote at negative pi. Let's keep going. What was the sine of 5 pi over 4? Negative root 2 over 2. So when we flip it, it's going to be a negative root 2. What was the sine of 3 pi over 4? So when you flip that, it's going to be negative 1. What about 7 pi over 4? So when you flip it, and what about it at 2 pi? What was the sign? So cosecant is going to be undefined. So we're going to have another asymptote at 2 pi, as well as
3 pi, right?
3 pi, 4 pi, 5 pi. Yep. What about over here in the negative? There we go. Okay. So at pi over 2, we're at 1. At 3 pi over 2, we're at negative 1. Okay. And then we're at a root 2. Now, root 2 is actually a number that's a little bit bigger than 1. Okay? Oh, I forgot. Let's do one more. Let's do 0. What's the sign of 0? So, if the sign of 0 is 0, then the cosecant is going to be undefined. So we're going to have an asymptote. Yeah, it does. Yeah, it does follow a pattern. Everything does follow a pattern. Now to graph the rest of cosecant, because these ones here, square root 2 is a little bit bigger than 1. We do have some asymptotes involved. The easiest way to graph a cosecant function or a secant function is to graph their original, their reciprocals. Secant with sine, right? You have the picture of sine on the other side, on the other flap, right? It went up and then down again, and then it went up, correct? Do you see how sine, the maximum on sine is a point actually on cosecant? And then the minimum of sine is actually a point on cosecant. Does everybody see that? Okay. Well, the square root of 2, the number is a little bit bigger than 1. So that's those. What's going to happen is that cosecant is actually going to go through these points and then approach the asymptote, get really close, but never cross or touch. And mine is touching because my pen is not calibrated, but yours should not touch. So when you draw, make sure yours does not touch. That is part of cosecant. It works the same way over here. The cosecant of pi over 4, 5 pi over 4 is a negative square root of 2. Over here, negative square root of 2. It's going to do the same thing. Get really close to the asymptote, but never cross or touch. And that is one period of cosecant. The period is one, I guess you could say like quadratic going up and one quadratic going down. Okay? I want to repeat the same thing on the other side. Okay? You have sine right beside you. Then we go down, and then up some more, and then down. That was the rest of sine, correct?
Right.
So wherever there's a min, that's the point on cosecant, and we're going to go down. Whenever there's a max, there's a point on cosecant, and we're going to go up. And there we go. The orange is the graph of cosecant x. So what will be the domain? What will be the domain of cosecant? The orange. Is it all real numbers? Negative infinity to infinity? Okay, so it's all real numbers except multiples of pi. How do we represent multiples of pi? We did this pi n. Yeah, so I'm going to do it the set notation way. All the x values such that x is not multiples of pi. So pi here. Now the one thing about cosecant, it doesn't have an amplitude, okay? Because there's no maximum point, there's no minimum point that we can, add together, divide by 2 to actually figure out, what the amplitude is. So there is no amplitude. So there will never be an amplitude. Zeros. Zeros is another word for zeros is?
Roots.
Roots. Another word for roots is? Zeros, where it crosses the x-axis. X-intercepts. Do we have any x-intercepts? No, so there are none there. All right? Now, if you have a look, our relative maximum, where are our maximums? Our maximums occur here and here. Where else? Those are maximums. Max. Highest.
Oh, yeah.
So how would I represent this? I'm not going to have just one. I'm going to have infinitely many. Where are they going to occur?
Every pi.
No, not every pi over 2, because here's a pi over 2, but I have a min here.
2 pi.
Every 2 pi?
Over 2.
Is that? Not be every pi, so it actually wouldn't necessarily work. Every 2 pi. From here to here, isn't this 2 pi? A half, another half, another half, another half. Okay. It occurs every 2 pi, starting where? At 0?
Negative 1.
You can say negative pi over 2, or you can say 3 pi over 2. Either one would work. And every 2 pi, that would be 2 in pi. That's where relative max occurs.
I have a question.
Yes.
How is that your max and not your min?
Well, your min will be here, and then everything going up, like a low point. Think about like with the quadratic. Remember how we had these versus these, and this was the min and this was the max. Same type of concept.
It's like the same. It's like they're all different graphs when they're in an asymptote.
Correct. Keeping with the whole idea of relative, what about relative mins? How often do they occur?
Wouldn't it be the same thing?
But are we starting at negative power 2?
No, it's like at -3 pi.
We can say negative 3 power 2, we can say positive power 2, and it occurs every 2 and pi. What about our asymptotes? Where do our asymptotes occur?
Every pi.
Every pi.
Starting at 0.
Starting at 0, so we could say it is
0. 0 pi.
0 plus pi n.
0 plus pi n, or we just say pi n. We can put 0. Oh, we kind of wrong, we said 0.
Is there some patient one kind of factor with the starting purpose?
Yes, but this is just based off of your basic.
Oh, the default.
Mhm. Yes.
Okay, so give me what you're saying over there.
Because since it continues even after 2 pi and way before negative 2 pi, it's going to keep going. So basically, every time you go a full 2 pi radians, you're going to end up at another maximum or another minimum. Yes. All right. So like if you look here at this particular point, right, this is a negative power 2. The next one doesn't occur until 3 power 2. That is a distance. Like if you subtract the two where they're located. That is 2 pi radians. So at the every 2 pi radians, the next one will occur. And then the next one, the next one.
Why isn't it plus or minus?
Because n could be any integer. Integers are
Positive.
positive and negative. Period. How long is it before the cycle starts to repeat itself?
Every pi.
2 pi. Because you have one going up and then one going down, and then you have another one going up. So that happens between every 2 pi. No, but see, it's, even though it's separate, it's not the exact same. It's where it starts to repeat itself. And the last one, the range. Is it all real numbers? Negative infinity to negative 1. Is the negative 1 included?
And then 1 to a positive.
And then 1 to positive infinity. Yes, sir. And that is cosecant. That is cosecant. Questions on that one? Secant goes with
Cosine.
cosine. Okay? What is the cosine of 0? 1. So when you flip it, that turns to what?
1.
Still 1. Because if you have 1 over 1, no, this is like the x values. And for whatever reason, remember 0 wasn't a part of it. I'll make sure 0 is a part of it. What was the cosine of power 4?
The square root of 2 over 2.
So when you flip it, for secant, that's going to be root 2.
Yeah.
What was the cosine of power 2? So the secant would be
0.
undefined. Because think about it, you have 0 over 1, flip it is 1 over 0. Which means there's going to be a what at power 2? A vertical asymptote. The cosine of 3 power 4? So then on secant would be negative root 2. And it kind of repeats the same pattern. The cosine of pi was? So when you flip that, that turns into negative 1. The cosine of 5 power 4? So then on secant it would be, everyone kind of following? Okay. A cosine, undefined, 7 power 4, and at 2 pi, it'd be 1. So I have asymptotes at pi over 2, 3 pi over 2, where else? Negative pi over 2, and negative 3 pi over 2. So my asymptotes occur every
2 pi.
how far apart are they?
Pi.
Pi. So they occur every pi, but starting starting where? Not at 0, at her
Pi over 2.
pi over 2. Alright? So real quick, I'm going to graph cosine, just so you guys can see it. It doesn't have to be, but I'm just kind of, I don't want you guys to get distracted by it. So I'm just using it as a guide. So just like with cosecant, secant works the same way. Wherever there's a max, wherever there's a high point on cosine, there's a minimum on secant. It does the same thing. Wherever there's a low point on cosine, there's a maximum on secant. It works the same way. Here's another high point at 2 pi. And you know, clearly if I kept going, it would just be, like that on the other side. Okay? So again, wherever there's a low point, there's a little maximum. Where there's a high point, there's a minimum. Mm-hmm. Do I have any zeros?
Nope.
What am I asking? What's my amplitude? There's none. It's just like cosecant. What's the period? 2 pi. Because remember, it's just reciprocals of sine and cosine. So it still has the same period as them. And the range? The negative 1, included or not included? And
1 included. That's pi.
that's pi. Infinity.
Oh,
We're about to use it again. The domain is all real numbers.
no, x, set of x not equal n of pi over 2.
Not n pi over 2. Because if I use n pi over 2, if I plugged in 2, that would give me pi. It's actually defining pi. No, it's not 2 pi. Think about it. The asymptotes, right? It makes the function undefined there. But it's defined everywhere else, correct? So the domain is everywhere it's defined except where it's not.
Pi over 2 plus n pi.
Pi over 2 plus n pi. Our relative maximums are actually now at every pi spread out by how many? 2 pi. And our mins, where are they? Every 2 pi, starting at
0.
say 0. So every 2 pi, starting at 0. Say 0 plus 2 n pi, or you can just say just 2 n pi. Say this. Graphing them, you've been doing it. You really have. When you graph sine and cosine, all right, all you got to do is just draw in the asymptotes. Wherever there's a high point, draw a min. Where there's low point, draw a max. Okay? So if you look at your notes, looking at this one, cosecant of x plus pi over 2. To graph this, you're going to graph this reciprocal. What's the reciprocal of cosecant? Sine. So this is actually what you're going to graph. You're going to graph this function instead. Okay? You're going to graph this function instead. So, let's make our quick little table. What's happening to my x's? Phase shift, pi over 2, left or right? So is that positive or negative?
Negative.
Negative. Anything happen to my y's?
No.
Nothing. So sine starts at 0 or 1? 0. And then the big 5. So when you minus pi, 0 goes to what? Negative pi over 2. This one goes to 0. This one goes to pi over 2. This one goes to pi. And this one goes to 3 pi over 2. So you graph this. Okay? Graph this. 0, 1, 0, negative 1, 0. And yes, I know there's not like an extra add-in, just kind of slide that back a little bit on your paper.
Is that 5 or 2 the one that's on our paper? Negative 5?
So you got to draw that one in. So I'm going to dot this because that's not the graph that is asking me to graph. It's asking me to graph cosecant. So cosecant, it has asymptotes and it has basically parabolas everywhere. Wherever there's an x-intercept, there's an asymptote. So at every x-intercept that's on the sine graph, you need to draw in an asymptote. Is everybody with me? And wherever there's a high point, you have a what? A min. Wherever there's a low point, and the red is the graph of cosecant x plus pi over 2. For your homework, you're going to graph 3 functions, okay? This is one of the functions, so write down this equation on your paper. This is one of your functions, so write this equation down on your paper that you're going to graph. All right? This one I'm going to do on the video, so don't worry about that one, okay? This one you're going to graph on your own. All right, and you're also going to graph this one. So make sure that you watch the video so you can see one of me doing it with secant, and then the 3 that I said that you're going to do for homework, I want you guys to do those. So this is the one that I said I was going to graph so you guys can see one of secant being done, okay? Secant is the reciprocal of cosine. So basically what I'm going to do is I'm going to graph 2 cosine x plus 1 and use that as a guide to graph the function that I'm actually wanting to graph. So I'm going to make my table, and it turns out that the only things that are being affected are my y's. I'm going to multiply all my y's by 2 and then add 1 to them. So my x's stay the same, but my y's, and I'll start at 1, get multiplied by 2, and then I add 1. So then that will be 3, 1, negative 1, 1, and then 3 after I do all that. So I'm going to do this in a very light pink because I don't want that to like mess you guys up. I'm just using it as a guide. So 0, 3, pi over 2, 1, pi negative 1, 3 pi over 2, 1, and then 2 pi 3. And I forgot 2 pi over here. Okay? So then I'm going to connect all those with a nice little dotted line. And then I'm using that as a guide. Wherever there's an x-intercept, there's an asymptote. And then wherever there's a high point, I'm going to do a little parabola pointing up, low point, a parabola pointing down. Now, if you notice, yes, these are the x-intercepts, but they're the x-intercepts after the graph got moved up. So I want to figure out what were the x-intercepts before I moved the graph up, because that is where my asymptotes are, okay? Well, since I moved my graph up, that technically meant that my midline was right here at 1. So wherever the curve crosses 1 is actually where my asymptotes are, okay? Because had I not moved it up, the graph up, those would have been my original x-intercepts, okay? But because it got moved up, they changed. But that is still where my asymptotes are going to occur, okay? So you can almost treat it as whatever D is, that is where your asymptotes are, okay? So whatever D is, which was 1, that is exactly where your asymptotes are, where the curve crosses that point. So now wherever I have a high point, I'm going to draw a parabola going up. Wherever I have a low point, I draw a parabola pointing down. And that is how you graph secant, okay? So you're doing those 3 problems that I had before I went over this example. I want you guys to give it a try, and any questions that you have, bring to class, our next class.